Hey, how's everybody doing? Can y'all hear me?
Hmm.
Yeah,
Yeah.
we can hear you.
Okay, cool.
Uh,
Yeah, we'll wait a couple more minutes and then we'll start up. Have all y'all signed into a WebAssign or have you done that yet?
um, I set up my account with WebAssign, logged in. I haven't done any of the core
Yeah, that's
work
fine.
yet.
Right, because today we're starting stuff up. Right. Yeah, that's okay.
I got stuff falling off my bookshelf.
All right, so I guess we'll get this show started. Can y'all hear me? Yes? No?
Yeah, we can hear you.
Okay, cool. All right, yeah, I'm Mr. Spire. I'll be your Calculus 1 instructor. Okay, so whenever we join these up or you join the Zoom meetings, just make sure that you're on mute. But if you have a question, while I'm explaining something, go ahead and unmute yourself and say, hey, can you repeat this, or do another example like that. And you can also type it into the chat window. I may miss that though while I'm lecturing, so probably the easiest thing to do is just go out there and say, hey, repeat this or whatever, as if we were in class or something. Now, if you haven't taken a look at the stuff on Canvas yet, please do so. So I'm going to share, what you guys will typically see on there. When you guys log into Canvas, right, you click on this course and stuff, take a look at all this information right here, especially stuff from the files tab. Like I have my addendum, which discusses the grade breakdowns. Here's the James Stewart book. I don't know if you all read that announcement that I had posted before, but you don't need to buy a physical book. This is just free for you all to download. Even though it is the 8th edition, it's the same as the 9th edition, which they use on Canvas. It's the same exact problems. I took this class when they were using the 4th edition, and that was like 20 years ago. Okay, so these problems have not changed. It's the same problems from back then. Calculus hasn't changed, right? It's not like those medical books or whatever, where every month they're finding some new discovery. Calculus has been the same for hundreds of years, right? So nothing new is in there. They just obviously want your money. But you will have to buy a code, correct? Some sort of student access code. And there's 2 options for that right there. If you click on the addendum, I described the pricing right here. If you notice, and this is done through WebAssign, you have a single term, $100, and then this one, $125. The single term basically gives you one shot, right? Like let's say you take the class now, you decide I'm gonna pay the $100 fine, or not the fine, it's not fine, the $100 access code. If you don't pass this semester, or for some reason you have to drop the class and repeat it the following semester, you would have to buy another code. Multi-term, they don't care. Like if some of you are engineering majors and stuff like that, or you need to take more math beyond Calculus 1, I would just go with the multi-term, because this will last you basically until you use the whole book. And you pretty much take Calculus 1, 2, multivariable, 3 math classes, with this same exact book right here. So I would go out there and go ahead and do the second option. Or if you have to repeat the class, it doesn't matter, because multi-term is good for the lifetime of the book. That just pretty much means as long as the school uses it, which we're going to be using for years to come. So if I were you guys, I would go with the multi-term right there. And of course there's the grade breakdown and everything. If you notice, test average, homework, midterm, and final, that all calculates to your final grade. Now, important, the midterm and the final, they are worth 60% of your grade, right? That's the bulk of it right there. For all your tests, you will have to use the Respondus lockdown browser. Okay, so that's something that you should activate. If you have not ever used it before, what you should probably do is, because we're going to be taking these tests under quizzes, is you want to go out there and try taking this practice quiz right here. You won't see all this stuff on your respective Canvas. You'll only see the ones that you have check marks, because I've published it, right? So don't sit there and say, I don't see all these things right here. Right now, if you go to your respective quizzes, you'll only see this one right here. But go out there and take this practice quiz. It's not worth anything. It's just to ensure that the lockdown browser and the webcam stuff is working out for you. If you're having issues, email me or see me during my office hours. What are my office hours? Because it's not, at the office. So if you go to the files tab, you'll notice there's a link. It says my Zoom hours right here. And all you got to do is just basically, here they are right here. The link is right here. You're just gonna have to copy and paste this into your web browser, and that'll take you straight to me right there. If you can't make it, during these times right here, send me an email, and then we can set up some other time, outside of it. But if you do that, if we make that appointment, please log on, right? All right, what else? The syllabus is right here. This pretty much gives you a breakdown of what we're going to be doing week by week, and it'll give you a rough estimate of when the test is coming up. Okay, so you notice I'm not going to do 2.1 because that's not necessary. I'm going to start at 2.2. But you'll see, oh, week 1 we have to do 3 sections, week 2 3 sections. Oh, a test will be coming up the 3rd week, so you'll always have a rough idea of when these things are coming up. If you notice though, it's not, some of these sections are faster than others. So even though class does meet from 4 to 6:15, many times we're not going to use the whole 2 hours and 15 minutes. So you don't have to sit there and think, oh man, I'm going to be sitting on my ass, for all this time. No, it's not, we're not going to be here the whole time like that, because there's enough spacing that, we have adequate time to cover everything and do, extra problems from the sections. As far as the test, if you're wondering what to study, how do I study for these tests? Well, if you can do the homeworks, right? And if you do the go over the lecture material and stuff like that, and even rewatch these lectures because they are being recorded, that serves as a review, right? And if you're comfortable with that, you'll easily be able to pass the test. I don't throw, curveball problems like, where the hell did this come from? We never did anything like that in class. We will always have done something similar in class to what's represented on the test, okay? And of course, the final exam is cumulative, which covers everything. There is a big final exam review, but you don't have to worry about that right now. Now, as far as the pages tab, what do we have right here? So here's the academic calendar, for like important dates for the final. How to sign up for WebAssign if you have not done that. Professor Leonard is just a guy on YouTube, a teacher. Maybe some of you have heard of him. He has amazing videos. He has all kinds of lectures. If you click on him, a playlist will open up, and he has it very categorized, even up to calculus 3 and differential equations. So it's a good guy to keep, for future reference. So feel free to use him as well. And there is free online live tutoring. So basically, when we were in school able to have classes, there is a math tutor center, and the tutors are online via Zoom. It's just that they're on during specific times. Their Zoom links are right here. Make sure though that when you log into their sessions that you remember this password. They all have the same password. It's just 4 zeros. Okay. So if you need additional help, feel free to use them. They're there waiting. They're bored. So, entertain them with your problems. Now, something important that you all should look at is this trig review video. Because as I mentioned before in the announcements, a big thing that kills people in calculus is it's not even the calculus part. They get that part right. It's all the steps beneath it. It's the algebra, the factoring, the trig. It's even the signs. Some people may forget a negative times a negative is a positive, and they say negative instead, and then that throws, now you have the wrong answer, right? And it's like you shouldn't have gotten that wrong answer because of an arithmetic mistake like that. So we need to please go over that trig review video if you want a brush up on that. Another good resource is this right here, topics you should know before calculus 1. This guy, his name's Paul, not me. I didn't make this, but it's called Paul's Online Notes. If you haven't checked this out, definitely look at it because this guy covers everything, anything, all kinds of math. So you see classes, calculus 1, 2, 3. It's very organized. You see that right there? He's got all the sections. He has practice problems. He explains everything. So again, if you need more help or you just want additional problems, come to this guy's page. He's amazing. Keep him for future reference. Definitely bookmark it, into your own web browsers as well. So any questions so far before we actually start some lecture stuff, or no? No?
I'm just curious about why no graphing calculator suddenly.
I mean, that's been like that for years. I mean, it's been like that for a few semesters, and it just because what's happened is students just don't know what's going on, and they're just trying to throw everything into the graphing calculator, and they're not really understanding what they're doing. And in some classes, we do allow like statistics, for example, because of like the binomial distribution and certain creating linear regression and stuff like that. You can do that by hand, but it's just so tedious and it's just a waste of time. But yeah, it's just we want the students to understand how to do the material. And in other universities, they don't allow graphing calculators as well. I mean, when I took the Calc 1, 2, and all that stuff at UNO, they didn't allow graphing calculators at all. But you won't really need it, okay? And even though it is important that you recognize the graphs, of common functions, like x squared parabola, for example, you should still be able to realize what they look like. Again, if you don't know or you don't remember what they look like, you can always check out Paul's online notes, and he'll have those graphs right there. Anything else? Or no? No? Okay. All right. I'm just trying to get this aligned. Okay. All right, so basically, calculus 1, it has three important things that we're going to talk about. Three main things. The first thing are limits, and then the second thing are derivatives, and then the third thing will wind up being antiderivatives, the opposite of derivatives, but they're also called like integrals. All right, so section 2.2 is kind of like, bare introduction, the limits. So what is a limit? Pretty much a limit describes how y behaves as x approaches a given value, and we're just going to call that given value a, like that. So what's really important to note is that you can kind of think of a limit as, as y behaves as x approaches a given value a. What are you talking about? They're talking about the journey. Like if you were to keep walking towards that number, where would your y value eventually wind up at? That's what they're asking for. So it's not like what is it equal to? It says you get closer and closer to that specific x value. Where is the y going? And there's notation that we have for this right here. You'll usually see it like this, like the limit, and they'll have this. So that would be the limit as x approaches a of f of x is equal to some limiting value right here. So the limit as x approaches a of f of x is equal to some value. So basically what you're doing before we start doing it algebraically is we test values, or we can close to a that's a crappy a, close to a but not equal to A. So how do we do that? Why do we do that? Remember, I'll always post these on Canvas under the Files tab. These lectures, video lectures after we're done with class. If you missed something, please go back and watch the video. So let's check out a problem. Like, let's say we want to find the limit as x approaches 2 of x squared plus 3, for example. Or, yeah, x squared plus 2, for example. Something like that. Now, graphically, what is this thing right here? I mean, we could say, oh, just a rough sketch. If I were to draw this out, this is a parabola, right? X squared, that's a U-shaped function. This is a vertical shift, correct? So it looks something kind of like this right here. So what are we looking for? We're asking, as we get closer to 2, x equals 2. Let's draw this out more to make it look a little better. As x gets closer and closer to 2, where's my y value going, right? So basically we're walking to 2, like right here. And from here, right? We're not asking what happens when x equals 2. We're asking about the journey as we're heading towards 2. And if you notice, I drew these 2 blue arrows coming from both directions right there. That is very important because from the previous little set of notes that I had right here. Remember, I said we want to test values close to A, but not quite equal to A. So what can we do right there? Well, we can make like a t-table, right? A in this case was the 2, right? That's our guy that we're trying to get to, right? But if we want to test values sufficiently close, well, what that means is we want to test stuff a little smaller than A and stuff a little bigger than A. So something, a couple values a little smaller than A could be like 1.9, for example, because that's slightly smaller than A. Or we could test 1.99, right? That's a little bigger than 1.9 and it's a little closer to 2, right? So that's something a little smaller than 2. Likewise, what about something a little bigger than 2 for x? So I could test, maybe 2.01 like that. And then we could also try 2.1. And again, those are values that are slightly bigger than this A value. Now, did I have to test the 1.99? No, I could use 1.99999. It's these values right here. I chose them. It's up to you to decide what you want to use. But if you notice, they are very, very close to 2, right? Not quite on 2, but very close. Now, what happens when we plug these values in? Okay, like if we were to plug in, oops, yeah. If we were to plug in 1.9, for example, what are we actually going to get right there for x? Let's see what happens. So let me grab output. So we get when x is 1.9, what am I doing? I'm jamming 1.9 into here, right? So you have, I'll just do it for this first one. You have 1.9 squared plus 2, and that gives you 5.61, right? And then if I do 1.99 squared plus 2, you get 5.96, like that. If I do 2.01 and evaluate the function at that value, we get 6.0401. Or if I do 2.1 squared plus 2, we get 6.41. Now, Why are we doing that right there? So if you notice, if we approach 2 from the left, this is from the left, correct? Like this is me approaching 2 from the left. Like say we're walking to 2 from the left side. This is me approaching 2 from the right, coming from the right. You're walking 2 from the right. If I approach 2 from the left, or values slightly smaller than 2 in this case, you notice that they're homing in on some value, right? They're getting close to some specific value. Like if I did, let's say, what if I did 1 point, let's just say I did this, like 1.99999, 4 nines like that. What will the y value be? Well, if I go ahead and I throw that into the function, you'll see that we wind up with 5.99960, blah, 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 like that. But if you notice, it's getting closer and closer to some specific value, just like approaching 2 from the right in this instance. It's getting smaller, but it's getting closer to some specific value. And it looks like it's closing in on 6, right? So you may be wondering, well, couldn't I have just plugged 2 in, right? Couldn't I have just plugged 2 into here? And I could have gotten 2 squared is 4 plus 2 is 6, and boom, be done. Yes, you could have done that in this instance, but that doesn't work for all problems, okay? I just went ahead and did this one because it's just for you guys to understand the process. So again, what we're doing is we're just trying to find the limit. That just means as x approaches some value of a. In this case, we were trying to find out where is y going as x gets close to 2. So again, what did we do? We chose x values a little smaller than it and x values a little bigger than it. And we're just trying to see, is it homing in? Are the y values homing in on the same value from both sides? If they are, then yes, we would have a limit. And in this case right here, we could say, oh, it's 6. There are instances where the limit won't exist, and we will look at that. There are instances where you think there's no way that the limit's going to exist, and they do exist. So let's check out some of those. But don't always think, yeah, I can just plug the number in. Questions, or if you can, please put it on mute, okay? Unless you have a question. Thanks. All right, let's check this one out now. All right, so now we have the limit as x approaches 9 of x minus 9 over the square root of x minus 3. Now you may be thinking, oh, I can just jam 9 in, right? Just like the last problem, we jammed 2 in. I could have done that and 4 popped out, right? That was I'm sorry, 6 popped out. That was totally fine. Right here, that little trick's not going to work, because what happens if you go ahead and just try to plug 9 in? Like, what if I say, oh, 9 minus 9 over this is what we have, right? And if you simplify that, you wind up with, 0 over, this is 3 minus 3, which is 0 over 0. But what is 0 over 0? Don't say it's 0, it's not. This is undefined, right? Remember, anytime you have a 0 in the bottom, you don't care what's happening up top. This makes the entire expression undefined. So we have a situation right here. This is where that method of choosing values sufficiently close to 9 in this case will help out. Now, do you have to do this big old t-table thing all the time? No, there are algebraic tricks that we're going to talk about very soon, where you can go out there and manipulate your equation to get rid of the problem in this case. When I say get rid of the problem or the issue, it's this square root of x minus 3. This is making it undefined, and that's what's causing the problem right here. We'll talk about that in a little bit, how to get rid of that kind of stuff algebraically. So what do we need to do right here? Well, let's look at our t-table again. And 9 is going to be our guy that we're trying to look at or get close to, correct? Get close to that. So let's say, for example, I'm going to test 8.7, 8.8, 8.9. You know, values slightly smaller than 9. And then if I want to test stuff a little larger than 9, maybe 9.01, 9.1. Oops, you guys can't see.
Thank you.
Yeah, if you guys can't see anything, please let me know. Oh, hold on. All right, so what are we basically doing? We're plugging these x values into this function, right? Wherever we see x. So remember, you would plug in 8.7 right here, and then 8.7 in right here. I'm just gonna go out there and give you the y values. So when x is 8.7, y is 5.94. When x is 8.8, we get 5.966. When it's 8.9, we get 5.98. This is undefined right here, right? Undefined. Because we wind up with 0 in the denominator. When x is 9.01, we get 6.001. When x is 9.1, we wind up with 6.01. So again, we chose values slightly smaller than 9 and slightly bigger than 9. Remember, a limit's about the journey. If you're getting closer to that x value that we were trying to go to, where is the y value approaching? Not what is it equal to. Approach and equal are two different things. Approaching is like you're getting closer and closer, right? Equal is if you could somehow land right exactly on top of it, right there. But the trick to doing this again is you have to go out there and take values slightly smaller than your a and slightly bigger. Now you notice in this case right here, when we approach 9 from the left side, right? Correct? This is coming from the left. It's getting closer and closer to 6. Just like when we approach 9 from the right side, it's also getting closer and closer to 6. So you could say, since the y values are getting closer to 6. From both sides. That's very important, okay? So since the y values are approaching 6 from both sides, meaning something a little smaller than 9, something a little bigger than 9, we could say that the limit does exist. So limit is equal to 6 in this case. So what if we looked at the graph of this function right here? We'll just look at the graph and we're just going to investigate and see what it looks like. You're not responsible for knowing what this graph looks like, but it just helps to see as a visual. Do y'all see this Desmos graphing calculator thing? Can y'all see that?
Yeah, we do.
Okay.
Yeah.
All right, so this is what the graph looks like. It looks very similar to a root function. Now, again, we're looking at the limit as x approaches 9. So x approaches 9. Like if you zoom in, you can see we're getting some kind of value right here. If this is x equals 9, right, we can go up right here. Where's that respective y value? You can see, oh yeah, that it is 6, right? And as we walk along our graph from the left side, it's getting closer to y equals 6. Likewise, as I walk towards y equals 9 from the, x equals 9 from the right side, it's all also approaching that same value right there. And if we were to zoom in hard enough, like if I could zoom in forever, never, never, there would actually be an open circle right there. Remember, open circles means not included, and solid circles means that it is included. Because at this point right here, again, if you dump 9 in directly, we get undefined. So for that one instant, your line would just basically blip out of existence at x equals 9. But the limit still does exist because remember, limits are about the journey. If you were to approach 9, x equals 9 in this case, your y value is approaching, what is it, 6. All right, let's see. But what about like a nice old, like a trig problem? So we have the limit as x approaches 0 of sine x over x, something like that. So with this, we have an issue, right? Because if we dump 0 in, you get basically sine of 0, which is 0 over 0. No good, right? This is undefined. Now, undefined is a possible limit as an answer. It just depends on what's happening. So far what we've seen is that as we approach some specific x value, what we're trying to see is, do the y values home in on the same value from both the left side of this number and the right side of that number. So let's see what happens right here. So again, we want to choose stuff, close to 0 in this instance. If I choose something like, say, negative 0.01, negative 0.001. So these are getting closer and closer to 0, right? Negative 0.001 is slightly closer than negative 0.01, right? This is the hundredths place. This is the thousandths. This is negative 1,000th. So yeah, it's a lot smaller than this one right here. Same thing on the other side. If I want to choose, say, point 0.01, or I'm sorry, yeah, 0.001, and then also 0.01. Again, these x values, I'm just choosing them. It's up to you to make them up, but usually you want them to be, symmetric if possible, right? Just opposites of each other. Again, we can't even directly plug 0 in because we get undefined. Now, if we plug in negative 0.01 into our function right here for x, what do we get from a y value? You get actually 0.999. So this you just, physically type into your calculator. If I plug in the next one, we get 0.9999. You notice, oh, it's definitely, it looks like it's getting closer to 1, right? Let's see what's happening on the other side. Well, if you plug 0.001 in, guess what? You also get 0.9999. You basically get 4 nines, 0.01. That's going to give you 0.999. So in this case right here, even though when we initially looked at the problem, yeah, we had that issue. Oh, it's undefined. Why? Because you're dividing by 0. Remember, anytime you get anything divided by 0, it doesn't matter what you're doing, game over for that problem. It just, that expression is undefined. But that's not the limit in this case. Why is this not the limit in this case? The limit does exist in this case. The limit is approaching 1, right? Because as you can see, look, the closer I get to 0 from the left side, it's approaching 1. The closer I get to 0 from the right side, it's getting closer to 1, like that. So your limit is actually equal to 1 in this instance. So again, don't always think, oh, I can just throw the number in like the first problem and out it's going to pop out an answer. Unfortunately, it doesn't work like that 100% of the time. Usually it rarely works out like that. But let's take a look at another little trig one. Remember, if you're not comfortable with trig, check out that review video that is on Canvas under the Files tab and Paul's online notes. And before I do that, let's just look at the graph of this function, this sine of x over x. So remember, we were being asked, what is the limit as x approaches 0? So if we, come in to x equals 0, notice where's your curve approaching the y value from the left side. As we come in from the left, correct, towards x equals 0, you'll see, oh yeah, my y is getting closer and closer to the 1 right here. Likewise, the same thing can be said if we're approaching x equals 0 from the right side. It's also getting closer and closer to y equals 1 in that instance. Now, what if we take a look at the limit as x approaches 0 of sine of pi over x? Now this one right here, I'm going to show you the graph because this is just a very unique case, but it is something that does happen. Okay, I just want to show you the graph because there are some problems that we're going to be working where they don't give you a function like this. They give you the picture of the graph, and then you need to understand it's going to resemble a certain shape. So I just want you guys to recognize that right there. Now, if we look at the graph of this thing, what is going to happen right here? So remember, we have the limit as x approaches 0 of sine of pi all right, so as you can see, it looks very odd, right? So remember, we're trying to investigate what's happening as x gets closer and closer to 0, right? As we have, so if I keep zooming in on this right here, you'll notice that it looks like it's just getting super erratic, right? It's bouncing up and down faster and faster and faster as x approaches 0. Same thing from the right side right here. Whenever basically it's doing the same thing as the left side, but it's not symmetric at all. It's bouncing, or we say it's oscillating between two different values right here. It's whenever you see something like this where a curve looks super bunched up and it's getting squeezed together, what that tells you is that your curve is oscillating very rapidly between multiple values. In this case right here, it's oscillating between -1 and 1. So what does that mean? All right, so our graph was basically this right here. -1 and 1. So basically, as we got closer and closer to 0, our curve began to bounce really quickly between -1 and 1. And then as I went away from x equals 0, it kind of got wider as time goes on. But when you see, again, something like this right here, some squish on a curve like this graphically, it means that it's oscillating.
Mr. Sparks?
Your mic just got really quiet.
Hello?
Yeah, it's messing up.
Can you hear me?
No, we can't hear you.
Is it better now or what?
No, I still can't really hear you.
Hello? Better or no?
No, it's not better. It's
You
making
sound far away.
I mean, I'm talking right into this thing, so. What about now?
Yeah, that's a lot
Yeah.
better.
Better? Okay. All right, so yeah, I'll start back from here. This is where I probably lost the connection, right? Or just got bad. Okay, so again, when y'all are seeing some kind of squishing action happening on a graph, on a curve, what that means is your function is it's bouncing really rapidly between two y values. In this case right here, it's oscillating between, so when I put b/t, okay, that means between y equals -1 and 1 as x approaches 0. So we kind of have a problem right there, because remember, for that limit to exist, right, it has to be approaching the same value, same singular value from the left side of that x value and the right side. But in this case right here, that's not happening, because again of the oscillation right there. So since they're not convening on the same exact y value, since the y values aren't the same as we approach x from both sides, we say that the limit does not exist. Or basically, shorthand, you just say D and E like that. Like on WebAssign, they'll say just type in D&E if the limit does not exist. Again, the reason why I showed you all this problem graphically is because you're not going to be asked to figure out one like this algebraically or with a t-table. You may see something like this, not you may, you will see graphs like this where you'll see this squishing action. And again, when you see this squishing action where it gets like compressed like a spring or whatever, that indicates that it's oscillating or it's getting squeezed between two y values. And if it is getting squeezed, then that tells you, oh, the limit is not going to exist. Why does the limit not exist again? It's because we're not getting the same y values as we approach 0 from this case from the left side as the same y values as we approach 0 from the right hand side. All right, so again, if you don't get the same y value as you approach x from the left and the right of it, if they're not the same y values like we've been seeing with previous problems, then the limit does not exist right there. So if you notice, we've been talking about this limit as x approaches some value of a from the left and the right hand side. It is possible to have one-sided limits. So basically what that means is you're approaching your a either from the left side or the right side. Like you might, if you took Math 130, you'll probably see that this is kind of familiar right here. Like we have a left-sided limit. It would look like this. The limit as x approaches a from the left. Y'all remember that little negative sign? That means from the left. That doesn't mean negative a. If it was negative a, the negative would appear right here, right? And then we can also have a right-sided one. The notation for that is the limit as x approaches a, and remember that little plus sign like that of f of x is equal to L, or some limit like that. Now, if we combine these two, which we have been doing with the past few problems, because remember we were talking about this journey, right? Oh, as x approaches a. So basically, if I get the same y value approaching a from the left and from the right, we can say that the limit exists. So we could say, oh, the limit as x approaches a of f of x is equal to L if and only if and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches, oops, sorry, no, that's right, yeah, the limit exists if the limit as x approaches a of f of x exist if the limit as x approaches a from the left of f of x is also equal to the limit as x approaches a from the right of f of x. And again, that's just stating what we looked at graphically, right? So let us try out or apply this right here and see what happens. All right, so say we have this random sketch right here. Now, and we're being asked to identify the limits. So we don't have any graphs, any equations or functions. We can't plug values in because we don't have, again, an equation. We just have to eyeball this thing and look. But we need to, how are we going to figure that out though? So remember we just talked about a limit only exists if the y values match as we approach that particular x value from both the left side and the right side. If those y values are equal, then yes, we have a limit. If they are not equal, we do not have a limit, and in that case, it would not exist. So how do we do that for this particular first problem right here? This is saying the limit as x approaches 1 of f of x. We're being asked, hey, does it exist? If so, what's the number? If not, it does not exist. So we're kind of basically breaking it down into two smaller problems, a left-sided limit problem and a right-sided. So what you're asking yourself is, does the limit as x approaches 1 from the left-hand side of f of x equal the limit as x approaches 1 from the right side of f of x? That's what we're trying to see right here. So remember, the y value's got to be the same as you approach x from the left and x from the right, that particular x value. So if we were to work this out, right, like if we said, oh, if we were just being asked, what's the limit as x approaches 1 from the left? So remember, here's x equals 1. If you're approaching it from the left side, you're coming at it from this direction right here. This is 1 from the left. This is 1 from the left. If you approach 1 from the left, where's your y value going with respect to the curve? It's going to positive 3. Y'all see that? Because I'm basically going up to here. That's y equals 3. Now, if we look at the limit as x approaches 1 from the right, that is this. So basically coming at it from this direction right here. Because this is positive 1, but imagine you're walking to it from the right. Where's your line at with respect to y? It's heading towards y equals 1. So we have this. Does 3 equal 1? No, right? This is not true. So the limit in this case does not exist. Now you may be wondering, does that solid circle make a difference with the limit right here? No, not with the limits. Okay, because remember, the limit, all it cares about is, are we approaching the same y value as we approach that particular x value from both the left and the right direction? If they don't approach the same value, that limit does not exist. Now, what if we tried the second one right here, as x approaches 5? Again, we can break it down into two smaller problems. Maybe you have the answer already and you can see it. But yeah, basically what we're doing is we're breaking them down into two smaller limit problems, or two smaller one-sided limit problems. So you're basically saying, oh, does the limit as x approaches 5 from the left of f of x equal the limit as x approaches 5 from the right of f of x? So are these equal right here? That's what we want to know. So if we actually work that out, the limit as x approaches 5 from the left. Well, 5 from the left, here's 5, right? Correct? X equals 5. If we approach 5 from the left, that's us going in this direction, like that. We see that it's going to some y value. Don't sit there and go, oh, open circle means not included, so it can't be going to y equals, it's not going to y equals 2. It is. Remember, these open circles do not affect limits, all right? That affects if a particular value is equal to that. Remember, limits are not equal. It's about approaching that specific number. So as we approach x equals 5 from the left, our y value is approaching 2. Likewise, if we say, oh, What about if we approach 5 from the right? Like if I'll just do it like this. So if we approach 5 from the right, x equals 5 from the right, we're following this function right here. Where's the y value going? To 2 right there. Oops. So since the limit as x approaches 5 from the left is equal to the limit as x approaches 5 from the right, right? They're both the same values. We could say, yes, the limit does exist in this case, and it is 2. Remember, limits are about the journey, not what it is equal to. It's basically saying if you kept walking to that number, what would you eventually get to? So don't sit there and again and say, oh, this is an open circle. That means the limit does not exist. No. All right. Now, where would these open and closed circles come into play, right? Because they got to mean something, right? So remember, open circles means not included. Solid circles means that it is included or that it's equal to that value. Remember, equal is not the same as limit. Limit's about the journey. If you're walking to some value, where would you wind up? Okay, so if I were to ask you, say, for example, what is f of 1 in this case? Like if I just did that, this is where you start paying attention to, oh, do I have open circle or closed circles at those values? All right. So for f of 1, you notice we do have a solid circle. So that means we do have some value that it is equal to. Remember, equal to again does not mean limit. I know people think they mean the same thing, but it's not. Limit's about the journey of going there. This means when we say x equals a certain value, it means if I could step directly on it, would I land on some physical number? So in this case right here, we do have something, right? It would be 1 in this instance, because again, we have a solid circle right there. Now, what about if you were asked about f of 5, like that? In this case right here, it would be a does not exist. Why? Because you have an open circle right there. You remember when we're talking about functions and they say when x is equal to a certain number, they're asking you if you could somehow walk to the 5th step, what's the y value that you would land exactly on? You wouldn't land on any y value. That's like a hole, right? You would just fall to the center of the earth and through the earth and just keep falling. You can kind of think of it like that. With this one right here, if I could walk to x equals 1, I would land on y equals 1 because again, you have a solid circle. Now, can you ever have 2 solid circles be on the same x value? Like, could I have this right here where it's like, oh, these are both solids? No, that doesn't make any sense mathematically. So you can't have combinations of solid and open lying on the same x value. Or you can even have both open circles. Like this could be open as well. But you can never have 2 solid circles on the same x value. And of course, you can have an open circle like that. If there are no circles, okay, like say if they just said, hey, what's f of 3, right? Like just something like that right there. Well, you go to x equals 3 and we go up here. Is there any kind of solid, are there any kind of circles or anything like that, like open or closed? There's no open circle, but you can kind of say to yourself, well, if there's no open circle, there has to be a closed circle. So the line does exist right there. We could just say in this case right here, oh, it's like equal to 1.5, for example. So if you are asked to evaluate a function at some given x value and there's no solid or open circles around it, then it does exist. It's equal at that x value, right? At the x value right there. So you simply find out what its corresponding y value is and it's done. So I mentioned this because sometimes people, they get in the habit of, oh, I got to see circles everywhere. No, you don't. If you don't see a circle at that x value, at its respective y value, then it's automatically included. So it's automatically included. It will have an equal y value to its corresponding x value, like that. But remember, limits are about the journey as you walk towards that number from the left and from the right. When you are evaluating functions, it's almost as if saying when you are equal, like if you could physically land on top of that step, what would your y value be? Open circles, you would just fall through, does not exist. If you have a solid circle at one of those x values, or at that particular x value, the one with the solid circle, that's the y value that it's equal to. And like I mentioned before, you can never have two solid circles with this type of function. This type of function anyway is called a piecewise function. Why? Because it's just pieces of two different functions right there. All right, so let's try a couple more of these. All right, so here we go. Again, we have another piecewise function, right? We have open circles, closed circles. It's just a funky graph. So basically, they're trying to ask us all this information about 3, right? Or as x gets closer to 3, we have right-sided limit, or right-sided limit, a left-sided limit, right? We also have to evaluate the function. So remember, this reads as the limit as x approaches 3 from the right-hand side. Where's g of x going? Or where's the y value getting closer to? So x approaches 3 from the right. This is 3 from the right, correct? Remember, you want to imagine you are walking towards that x value from the right direction. So if I'm walking towards x equals 3 from the right, where's your y value going to? It's going to positive 3 right there. Now, if we do the next limit, this one, remember, this is a one-sided limit as well because it's asking from one particular direction. So this is saying the limit as x approaches 3 from the left. All right, so this is 3 from the left right here. So we're walking towards x equals 3 from the left-hand side. What's its respective y value that the line's going to? Well, that's going to be 1 in this case. Now the next one's asking, all right, this is not a one-sided limit. This is the plain Jane limit that we've been looking at since the beginning, right? Now this one's asking, what's the limit as x approaches 3 of g of x? Is it going to be 3 1, something else? What do y'all think it is? No guesses? Don't know? I'll guess, right? I guess I'll try. I'll raise my hand. Yeah, so remember, in order for a limit to exist, what has to be true? It has to approach, the limit has to approach the same y value from both the left side and the right side. Is that happening right here? No, because what's the limit as we approach 3 from the right? We got 3. What's the limit as we approach 3 from the left? We got 1. So we're getting 2 different values, right? 2 different y values as x approaches 3. They're not homing in on the same y value. So in this case right here, this does not exist. Again, it's because we are getting 2 different x values as you approach, 2 different y values as you approach this particular x value of 3. So again, if you're breaking it down into 2 one-sided limits. From the left of that particular number, from the right of that particular number. If the y values do not match, the limit does not exist. If they both were the same, then we would say, yes, the limit does exist, and it would be whatever that value is. So remember, limits are about the journey, right? If you were approaching that number, getting really close to it, not equal to, right? Like if you're able to step on it. Notice now right here, I'm asking for what is g of 3. This is where you're evaluating a function. So remember, what matters here is if you have open circles or closed circles. In this case right here at g of 3, we do have a solid circle. Remember, solid means included. So for that one instance, yes, it is equal. Again, don't say, oh, these are both open circles. It's not equal to. What matters is that you have a solid circle somewhere on that x value. So in this case, we have it at 2. So g of 3 in this instance is equal to 2. Now, what if this solid circle was an open circle, right? What if all 3 of these were open circles and you were asked about what is g of 3? Well, guess what? Your answer would be does not exist. Okay. Remember, in order for a limit to exist, right, this right here, you must have the same y values as you approach that particular x value from the left and the right hand side. If they are not equal, it does not exist. All right, we're gonna do another graph problem.
That's not a piss.
So these are just some of the problems from this. I'm just running out of space to write, but we'll finish it. We'll do them all. All right, so if you notice with this one right here, yeah, it is a piecewise function. You have open circles, closed circles. You have that squishing action happening right here. Remember, we looked at that at the beginning. That meant oscillating, right? We'll get to that in a little bit. But if we start with this right here, the limit as x approaches 3, 3 from, oh, I'm sorry, this is negative. These should be negatives. Sorry about that. Or no, hold on. Sorry about this. Should be 2 right here. I just copied it incorrectly. I was looking at another problem. Change this to 2, 2, negative 2, 2, negative. So change this to negative 2. Sorry about that. Negative 2 from the left. Negative 2 from the right.
It's negative 2.
And then this one's just plain old negative 2, and then f of negative 2. Change these for basically the ones in the black marker. Make note of that. Negative 2 from the left, negative 2 from the right, negative 2, and then f of negative 2. So these first two right here, these are one-sided limits. This is asking as x approaches negative 2, right here, this is negative 2, from the left side. Well, if we approach negative 2 from the left side, that's coming from this direction. Where's our y value going to? Your y value is going to 4 in that instance. Remember, it's about the journey, right? If we keep walking towards negative 2 from the left, we're walking up the hill towards y equals 4. Now, the next one's asking, what's the limit as f of x, or as x approaches negative 2 from the right of f of x? That's asking, okay, as we get closer and closer to negative 2 from the right, so this time we're coming at it from this direction, correct? So you're walking up the hill. Where are you walking up to? What y value is that? That is also 4. Now the next one is saying, what's the limit as x approaches -2? This is not a one-sided limit question. This is asking, does the limit exist at this one particular value? So remember, in order for a limit to exist at one value, it must be equal as you approach it from the left side and the right side. Now in this case right here, what happened when we approached -2 from the left? We got 4. When we approached -2 from the right, we also got 4. So that tells us that the limit does exist because they are equal. Remember the last problem that we did, we got 2 different numbers, right? And because we got 2 different numbers, the limit did not exist. But in this case, the left sided limit and the right sided limit are equal. And in this case, they are both 4. Now, the next question is saying, oh, what is f of -2? Evaluate this function at x equals -2. Does the line exist at that instance? Well, in this case, it does not. Why? Because where's x equals -2? It's right here. What's happening at -2? Oh, open circle. Remember, if you have an open circle, that means not included. For that instant, it's flipping out. Or you would fall into a hole if you were to actually walk straight and arrive at -2. So in this case, this does not exist. Now moving to the red ones, this is all talking about 0. What's happening at 0 in this case? So it says, oh, the limit as x approaches 0 from the left-hand side. So remember, this is 0, right? This is x equals 0. If we approach 0, x equals 0 from the left side, where are you coming at it from? From here, correct? Because we're walking towards x equals 0 from the left-hand side. Where's your y value getting closer to? In this case, it is 1. Because remember, we're walking towards x equals 0 from the left side. Now, if we approach 0 or try to find the limit as x approaches 0 from the right-hand side, what's going on right there? Well, you're walking to it from this direction. This is x approaches 0 from the right. Remember, you're walking to it from the right. So if we do that, our y value for our line, it's down here. What is that? That is -2 in this case. So the next question is, okay, what is the limit as x just approaches 0? Not a one-sided thing like 0 from the left or 0 from the right, but just if it approached 0. Remember, for a limit to exist, what must be true? The limit only exists or exists if we get the same y value as we approach that particular x value from the left side and the right side. Is that happening right here? No, because remember, when we approach 0 from the left, we got y equals 1. And then when we approach 0 from the right side, we got y equals -2. And because those two are not equal, the limit as x approaches 0 does not exist. Remember, it existed for the -2. Why? Because we got 4 when we approached -2 from the left and the right-hand side. Now let's evaluate the function at x is equal to 0. Remember, what's going to determine whether that value, or we have a value, it's if you have a solid circle at that particular x value. We do, right? We do have a solid circle at that particular x value. It's right here, this thing. Remember, that signifies that it's included. So yeah, we do have 1. The answer in this case is 1. If this was an open circle and this was an open circle, then the limit, f of 0 would not exist in that case. But because one of these circles was a solid circle, that winds up being the answer to this particular problem. Like I mentioned before, you will never have all solid circles at a particular x value. You can only have one solid circle at a particular x value. Okay? So there's still more questions to this problem. All right, now this is asking, this is not a one-sided limit, correct? We don't see a little plus sign or minus sign to indicate 2 from the left or 2 from the right. So basically it's just asking you what is the limit as we approach this number. But again, how do we figure that out? You can break it up into 2 smaller problems, right? As a left-sided limit and a right-sided limit problem. But remember, the gist of it is that what? A limit exists if we get the same y value as we approach that particular x value from the left side and the right side. So look, right here, if we approach 2 from the left, we can see, oh, it's basically going to y equals 3. If we approach 2 from the right-hand side, correct, it's also approaching y equals 3. So because it's approaching the same y value from both directions, meaning the left and the right-hand side, the limit does exist in this case, and it is y equals 3. If for some reason they were approaching different y values, like right here, right? Remember, as x approached 0, they were approaching different y values from the left and right-hand side. The limit would not exist in that case. Remember, at -2, the limit did exist because what was happening? They were approaching the same y value from the left side and the right side. Same concept. Now this is asking, what's f of 2? Remember, that's saying, oh, can we evaluate the function, this particular function, at that value? What matters is that, do you have an open circle or a solid circle at that point? If you have a solid circle, then yes, you can evaluate it. But if you have no solid circles whatsoever, you cannot. So at x equals 2, there's an open circle, right? That means it's not included. Not included means that it's not going to exist. If this was a solid circle, or it was just a regular line that ran right through x equals 2, that y value would be the answer. All right, f of x, or the limit as x approaches 5 from the right. Now, I did mention, oh yeah, remember when we had this oscillating stuff, that means it's bouncing between 2 values. But this is kind of tricky right here because this is oscillating from the left only. Why is it oscillating from the left only? Because it's only squishy from the left. From the right side, it is not oscillating. Okay, it's a nice straight line right there. So make sure y'all pay attention to that right there, because that will affect these two answers right here. So if we approach 5 from the left, this is us walking towards x equals 5 from the left. Remember, it's not squishing to the right of 5. If it was squishing to the right of 5, it would look like this, okay? You'd have this. If I had this right here instead, then that would indicate that, yes, it's oscillating to the right of 5, but it's not, though, in this case. So if you have a nice, curvy line like we do right here, it's not oscillating from that direction. So since it's not oscillating to the right of 5, coming at it from this direction right here, it is approaching some y value, and that y value is 3 in this instance. So remember, if you don't have a squishy line coming from one direction, then something is existing right there. But if you have a squishy line, like to the left of 5, that means it's oscillating right here. So for this one, as x approaches 5 from the left, it's not going to exist because it's oscillating between 4 and 2. Y equals 2 and y equals 4. All right, so now what we're going to check out are something called infinite limits. So if the values of f of x increase, W slash O means without, okay? If the values of f of x increase without bound, that means it just keeps going up forever as x approaches a. Then we can say, oh, the limit as x approaches a of f of x is equal to positive infinity. So basically, it's just like a line that goes up. You know, if you have something doing like this forever, or it just looks something like this, right? This line's just going up forever and ever, never towards positive infinity. There's nothing containing it at all or preventing it from bouncing back down or limiting its growth. And the same holds for the reverse, right? Like if the limit or if the values of f of x decrease without bound as x approaches a, then we can say the limit as x approaches a of f of x equals negative infinity. So that's kind of like, you know, if you have something doing this, for example, right? As I go towards as x goes further and further to the left, or as it gets smaller and smaller, your y value is decreasing forever and ever. It's going towards, you know, negative infinity. Likewise, as x gets bigger and bigger in this case, y would be going to positive infinity. And it just depends on your graph, what it's doing or how it's drawn, or how your function is behaving. So let's check out this function right here, or this rational. Sorry, did you copy it or no?
It's okay. I got
Yeah,
it.
sorry about that. Yeah. Remember these videos, I'm gonna post them on Canvas so you can go back and review it. Yeah, let me know if I'm erasing something, say stop, you know, yell it out. I know the board's just small, I know, yeah. All right, so if we look at this, remember how we first started out with the problems? We have an issue, right? Like I can't jam 4 in. Why? Because you get, you know, 1 over 4 minus 4, that's 1 over 0, which is undefined. Right? We have that little issue right there. So, you know, you can make a t-table. But if I just draw the graph out, I'll leave it up to you guys to draw the t-table or complete it. Remember what you would do is we have to choose numbers slightly smaller than 4 and stuff a little bigger than 4. So something slightly smaller, you could say, oh, 3.99 and 3.9, for example. Something a little bigger could be 4.01 and 4.1, something like that. And then you plug in your y values, and you would see that they could be homing in on something, or maybe not. Remember, if they both home in to the same y value from the left side and the right side, that would tell you that the limit does exist. If you're getting completely different numbers, then that tells you that the limit does not exist. So graphically, what's happening right here? So at 4, we don't have an x value. We don't have a y value that exists. But what your graph does wind up doing is it's doing something like this right here. So we don't have any open circles or closed circles at all. But we do have something weird happening, right? The line's not continuous. When I say it's not continuous at x equals 4. Continuous means you can basically draw your whole entire graph without lifting up your pen from the paper or marker from the board. That was impossible for me to do, right? Like I had to draw this and lift my marker up to go up here and continue to sketch. So that's not continuous right there. Now, coming back to, does the limit exist as x approaches 4? Well, what do we need to look at? We need to look at, are we getting the same y value as we approach 4 from the left and 4 from the right? Are we getting that right there? Well, let's see. Let's break this up, right? What we're looking for is, does the limit as x approaches 4 from the left of f of x equal the limit as x approaches 4 from the right of f of x? Big old question mark, right? Because if these two are true, or they're the same, sorry, not true, if they're the same, then the limit does exist. Well, what is the limit as x approaches 4 from the left? Well, we look at it as we walk towards 4 from the left-hand side. What do we have? An arrow going down forever. That means it's going down forever. What exists way down there forever and ever with respect to the y's? You get, this is negative infinity right here. So we have negative infinity as we approach 4 from the left. What about as we approach 4 from the right-hand side? Well, here's x equals 4. If we walk towards it from the right-hand side along this respective curve, where are we going? Up forever and ever and ever. Where's up there forever? Positive infinity. So what we mean by infinite limits, because there's nothing stopping it from going up forever or going down forever in this case. So we get positive infinity in this case. Now remember, in order for that limit to exist, the left-hand side limit must be equal to the right-hand side limit. Is infinity equal to negative? Is negative infinity equal to positive infinity? No, that's false. So does the limit exist right here? The limit does not exist. So what you would see right here is, if you were to plug these values in to your specific function or rational expression, you would see that the y values right here for 3.9 and 3.99, they would be getting super small. Like this might be negative 1,000. This would be negative 1,000,000. This one right here, as you get closer and closer to 4, this might be 1,000. This might be 1,000,000. So if your stuff is growing super large, that tells you right there, oh, it's probably going to positive infinity. Or if it's getting small super rapidly, meaning like the first y value is negative 10, the next y value is negative 1,000,000, and so on like that, that indicates it's going towards negative infinity. Coming back to this, the limit does not exist. Why? Because we're not getting the same y value as we approach 4 from the left-hand side and the right-hand side. It always comes back to that every single time. If they were both infinity, then we could say, yeah, it goes to infinity. Or if they're both negative infinity, we say it goes towards negative infinity. I'm just going to erase the top right here. Let's look at the limit as x approaches 2 of -1 over x minus 2 squared. So again, we have that issue of, can't slap 2 in there, right? I can't throw a 2 in because we would get 1 over 0, right? Which is, or -1 over 0, which is undefined. So again, you could go out there and do your little t-table and, choose numbers around 2. Stuff a little smaller, stuff a little bigger, right? Like you can test 1.9, 1.99, something a little bigger, 2.01, 2.1, for example, and you can plug the numbers in. This one's undefined right here. That's what would happen. You get error in your calculator if you plug that in. But graphically, what is this one looking like? Well, it's doing, it has this kind of shape right here. Now, again, if we were being asked to examine what is the limit as x approaches 2, let's break it up, right? Maybe you don't have to break it up. If you can see graphically what it's doing, that's fine. But yeah, what if we did? Again, we're looking at, does the limit as x approaches 2 from the left of f of x equal the limit as x approaches 2 from the right of f of x? Because that's what matters, right? If they're the same, then the limit exists. If they're different, the limit does not exist. Now, if we approach 2 from the left, here's x equals 2. If we approach 2 from the left, what's going on? We're dropping down. We're walking down the mountain forever and ever. If we keep walking down without bounds, where are we going? To negative infinity. Now, what happens as we approach 2 from the right? So we're walking along towards x equals 2 from the right. Where's our line going? Down, down forever without bound. So that means that is going to negative infinity. So remember, we were trying to ask, does the limit as x approaches 2 from the left also equal the limit as x approaches 2 from the right? Well, are they equal? Yep, they sure are, because what do we come up with? Negative infinity. So what is this weird thing that's happening right here, right? Because again, this graph isn't continuous right here, right? Because again, I had to lift up my marker to draw the rest of this curve. Well, there is something unique happening right here, right? I don't know if y'all remember from Math 130, but this is a vertical asymptote, right? Right here we have a vertical asymptote right here at x equals 2. Remember, vertical asymptotes are kind of like imaginary walls, or it's kind of like, oh, our line or curve does not exist at that one particular value for that instant. It gets super close, right? It's kind of like a wall, it's bounded. This thing's like an imaginary and invisible wall. It can cross it, but it cannot exist at that particular point. How did I find that, right? Did I just pull it out of thin air? No, algebraically, remember, how do you find a vertical asymptote from 130? It was because you had a restriction in the bottom. You set the denominator equal to 0. So like you don't care what's happening in the numerator, right? That's not gonna, this numerator can't be 0. It's the denominator that can't be 0. That's what makes it undefined. So you'd say x minus 2 squared equals 0. So really this squared right here doesn't affect anything. You could get rid of it algebraically by taking the square root of both sides, but then you get square root of 0, which is 0. And you're left with x minus 2 equals 0. And you're left with x equals 2. That's how you find the vertical asymptotes, right? Again, that comes from 130, math 130. You set the denominator equal to 0, and you go out there and you solve it. Sometimes you may have to factor, right? The denominators depends on what's going on. That is something, that you guys should remember. If not, remember, check out those Paul's online notes. That guy has tons of stuff for algebra, the calc stuff, everything, trig. All right, now we want to sketch the curve and use it to determine the values of A for which the limit, I'll put this right here, the limit as x approaches A of f of x does not exist. All right, so what are we working with right here? So this is a piecewise function, right? If you notice, there's 3 smaller functions right here, but how do we know which one we work with? Well, it's by these domain restrictions, right? This says if x is less than -1, use 1 plus x, or if x is between -1 and 1, use x squared, and if x is bigger than 1, use this 2 minus x right here. Remember, this means greater than or equal to. Equal to, these do not have bars, so that's not equal to. That's going to be very important when we graph this, because that's going to determine whether we have open or closed circles, right? All right, so how do we graph a piecewise function, right? 1 plus x if x is less than -1. Well, we can make like 3 little t-tables, right? Let's say if I do it for the 1 plus x, and I'm gonna make a t-table for that. Well, as far as choosing values, I can't choose like 10, right? Why not? Because it says right here, 1 plus x if x is less than -1. So I have to choose stuff smaller than -1. Like I can choose -1 and -2 and -3 even if I wanted to, right? But you may be asking yourself, wait a minute, didn't you say this means not equal to? So why can I use this right here? Well, we can use it. It's just that we're not going to have a solid circle at that value. We're going to have an open circle. So when x is equal to -1 right here, we get 0. And then when x is equal to -2, you get -1. So if we graph that -1, 0, that's right here. But remember, you're not going to have a solid circle. You're going to have an open circle. Why? Because there's no bar underneath this inequality sign right here. And then when x is -2, y is -1, so we have a dot. But our graph is pretty much showing this, right? The reason why I'm drawing an arrow right here is because there's nothing closing this off, right? It didn't say, oh, x is in between -1 and say -10, so I don't have to stop it at -10. It's just going down in this direction forever. Now, what about the x squared? Like, what if we do that one? So x squared says, well, we only exist, or x squared can only be used if x is in between -1 and 1. So with that t-table, I can choose -1, 0, and 1, right? Because that's another nice little number, 0. That's something else that we can use. Now, when x is equal to -1, what do we get? -1 squared, which is +1. And then when x is 0, 0 squared is 0. This is also 1 when x is equal to 1. Very important, though, when we graph it, look at what it's saying right here. It's saying this, remember, is saying when x is greater than or equal to -1, this chunk right here. Like if I flip this around, we get this, right? These two are equivalent right here. I just basically mirrored it over. It's the same thing. So really important, we have a bar underneath. That means included. So at -1, 1, we're going to have a solid circle right there. That's for the x squared function. Why? Because there's a bar underneath that inequality sign. And then the graph also runs through 0, 0, and it also runs through 1, 1. But at 1, 1, are we going to have a solid circle? No. Why? Because look at what it says. It says x is less than 1. It doesn't say x is less than or equal to 1. So that means open circle right there. Open circle at this point. So the x squared behaves or will look like this right here. And then if we do 2 minus x, if I can squeeze it in right here, this one says x is bigger than or equal to 1. So I'll just start with 1, 2, you can go 3, 4, 5, whatever. You just need a couple points right there. So I'm going to start at +1. So if I dump 1 into here, we get -1. If I dump 2 in, I get 0. And then so on like that. This is a straight line right here. So what would that look like graphically? Well, this says 1, -1. Here's that value right here. The question is, are we going to have an open circle or a solid circle at that point? You're going to have a solid. Why? Because this says bigger than or equal to 1. So it's going to look something like this right here. And then we have 2, 0. What's going to happen right there? I'm sorry, this is +1. My mistake. 2 minus 1 is 1, right? Yeah. So it looks kind of weird, right? We have you have an open circle from the red or the x squared, and then you have a solid circle from the 2 minus x. Is that possible? It sure is, but let's continue to draw the rest of this. So then we also have the next point, which is 2, 0. And this is not going to be open or closed circle at all. This is just a point. Basically, your curve is going to be doing this forever and ever and ever. It's decreasing also without bound because again, there's nothing. It never said, oh, x has to be between two x values like it did for x squared in this case. It just said if x is bigger than or equal to 1, use this guy right here. Remember, to graph a piecewise function, you're just going to make a bunch of t-tables, right? You can't just throw in any number, though. You have to throw in numbers that fit within the domain restrictions right here. So this is what it looks like. And remember, our directions were asking to determine the values of a for which the limit does not exist. So remember, for a limit to not exist, what has to be true? We have to have two different y values, right, as we approach a particular x value from both sides, right? So you're thinking, what how the hell do I do that? Where do I even look, right? Like, where do I even look for that? Well, the only places where you'll have issues with that is where you have open or closed circles, like a mixture of those. So there's two possibilities, right? Like we have an instance right here, like this is a spot where the limit may not exist, and also this is a spot where the limit may not exist. Why? Because again, it's where you're having these circle issues going on like that. Everywhere else on the graph, the thing exists, right? Don't look at, oh, does the limit exist as x approaches 3? Yeah, it does, because do you even have a circle there? No, if you don't have a circle, don't worry about it. Like even right here, nothing. It all exists right here. Again, the only issue or problem spots where a limit may potentially exist or has a chance to not exist is where you have solid circles, open circles, stuff like that. Let's look at x equals 2, or the limit as x equals 2 of f of x. That's a problem spot right there. I'm gonna erase this. That's a problem. I'm sorry, -1. What am I doing? -1. That's a problematic spot, or that's a potential where the limit may not exist. The other potential spot is limit as x approaches 1, right? Because that's another spot where you have open circles. So if we look at this first one, does the limit as x approaches -1 of f of x exist? Remember, in order for a limit to exist, what has to be true? It has to approach the same y value from both the left side of x and the right side. Is that happening right here? So does the limit as x approaches -1 from the right, or I'm sorry, -1 from the left of f of x equal the limit as x approaches -1 from the right of f of x? Is that going to be a true statement right there? Well, if we approach -1 from the left, or that's that blue line right here, where's your y value going or approaching to 0? Y equals 0 in that case. So we get 0 equals, what about as x approaches -1 from the right? Where is that y value approaching? Well, look, it's the red line this time. Where's the y value for the red line at x equals -1? Up here, that's 1. Does 0 equal 1? No, that's false. So what does that tell us about the limit as x approaches 2? I'm sorry, why not put 2? It's -1 right here, my mistake. -1, change that to -1. Everybody do that on your notes. Change this from 2 to -1. Change from 2 to -1. Make sure y'all fix that. So in this case right here, the limit as x approaches -1, it's a DNE, does not exist. Why? Because, again, we're getting two different y values as we approach -1 from the left and -1 from the right.
Right.
That's one of the answers right there. Or maybe that's the only answer. Remember the other problem spot that we have, or potential spot, is this other one where the limit as x approaches 1, correct? Because that's where you have circles. Remember, it's where we have the open or solid circles that could have a potential problem. So if we look at the limit as x approaches 1, this one right here, again, what are we looking for? We are looking for, you just break it up, right? Does the limit as x approach 1 from the left of f of x equal the limit as x approaches 1 from the right side of f of x? Are those two going to be equal, right? That's what we're looking for right there. So are they the same values, right? That's what matters in the end. Are they the same values? Well, if we approach 1 from the left, where's our red line going? The +1, correct? It's swooping up to x or y equals 1. Then as we approach 1 from the right, you're walking up this purple line, it's also approaching y equals 1. This is true. So this is not a problem right here. This is equal to 1. This is okay. Remember, our problem was, or the directions asking, it was asking which values of a does the limit not exist. So your final answer is at a approaches -1. I'm sorry, x approaches -1. Because remember, we were just looking for what's the value that the limit does not exist. Not the ones that it does exist, does not. So we were just trying to identify the problem, the problematic area or problematic point in which the limit does not exist. All right, so now what I'm gonna do is we're gonna go into 2-3. We're just gonna do like the first little chunk. I'm just gonna write down the limit laws, okay? And that way Wednesday, we can start with the problems. So the way we've been examining these limits when we had a function, it was very tedious, right? We're making a t-table, trying to find values a little smaller than that x value, a little larger than, and then we were trying to see, does it home in on a specific value? And it's tedious, right? Because you're sitting there plotting crap, wasting time. This next section is a lot better because it's trying to figure out the limits algebraically, which is 10 times faster, 1,000,000 times faster. All right, so with these limit laws, we just want to suppose that C is a constant and the limit as x approaches a of f of x, and the limit as x approaches a of g of x exists. Okay, suppose that. Then we can start manipulating things a little bit. So say we're adding up two different functions, right? Since they both exist, what we can do is just break it up and analyze, I'll say plus or minus, and we can analyze each one individually, kind of like the distributive property. And of course, if both the limits exist, like if you work this one and you got 2, and this one was 7, you say, oh, 2 plus 7 is 9. Or for subtraction, 2 minus 7 is negative 5. We will do a bunch of these problems next class for sure. I'm just writing down the laws right now. So if you have the limit as x approaches a of c times f of x, so that means a constant, right? Then constants, you're not evaluating a constant, you're evaluating a function, right? Functions have variables and stuff. So what you can do is just move that c out in the front and then multiply it into whatever the limit is. So again, it's kind of like distributive property. I'm just moving the c, or the multiplicative property, I'm just moving the constant out front, because that's not going to affect your final answer whether you do it first and multiply by the limit, or find the limit then multiply it by the constant. The third one is, what if we're multiplying, right? Like if I have the limit as x approaches a of f of x times g of x. So I could say, hey, it's the same thing as the limit as x approaches a of f of x times the limit as x approaches a of g of x. Same thing holds true for division, all that good stuff. Again, we can apply that limit to both the numerator and denominator. We have that. What if you have
Can you
exponents,
move the
right?
board up some?
What now?
Can you move the board up some? I can't see the.
Yeah.
Thank you.
Now, what if we have an exponent? Like, say we're taking the limit of some function where the whole thing's raised to some power of n. Well, what you can do is we can evaluate the limit of that function and then raise the whole thing to the power of n. So, like if you got some number, right? Like if the answer right here is 2, and then you square it or cube it, you wind up with 8. Right here, what would happen if the limit was 2 and I cubed it afterwards? I'd still get 8 right there. So exponents don't matter in that case. And like I said, we're going to do all kinds of these problems next class. Now, what if you don't even have a function at all? And you just have a constant, like the limit is x approaches a of a constant. That's just equal to whatever the constant is. That's the best one because there's no work involved. And the last one is the limit as x approaches a of the nth root of f of x. So it's kind of like number 5, because radicals and exponents, you can't write them in equivalent forms right there. So what would happen in that case is it's the same thing as saying the nth root of the limit as x approaches a of f of x. So it doesn't matter if you take the root of the function first, then evaluate the limit, or find the limit and then take the nth root. They are both equivalent right there.
What does number 5 say?
Oh, the limit as x approaches a of x f of x all raised to the nth power right there. So what this one's saying right here is, let's say we find the limit first, or what we do is we take the function, we evaluate it and raise it to the nth power and then take the limit. That's equal to you find the limit of the function first and then applying the exponent. So the order doesn't, it's basically saying the order doesn't matter in which you do it. Do I take the limit first and then apply the exponent? Or do I apply the exponent first and then take the limit? That's what these two are basically saying. Kind of like number 7. Number 7 says, do I take the root of the function first, then apply the limit? Or do I take the reverse of that? And again, the order doesn't matter because you'll still get the same answer. It's kind of like the same thing like you saying, well, if I go 2 times 3 or 3 times 2, am I going to get a different answer? No. The order doesn't matter in which you do it. You'll still arrive to the same result. So I know these rules, it seems like a lot of rules, but this is just algebra type stuff. And these problems are, I think our students find them way easier than the ones that we did from the previous section, because again, we're not doing T-table stuff. It's just algebra. And in these cases right here, you are allowed to just pop the numbers in and evaluate the expressions. But if you have an issue where we get some kind of undefined thing, then the goal is to try to algebraically manipulate the expression so that we don't have an issue anymore. And that's why it's so much better, because you're not doing T-table stuff and plugging numbers in. So we shall stop here for today. Like I said, I'm going to upload this lecture into Canvas right now. So if you missed something or you came in late, please go back and check it out. If you have questions on things, you're looking over stuff or you're trying to work the homeworks, remember I have those Zoom office hours. They are posted on Canvas, okay? And I'll be on there tomorrow, all those days listed Monday through Friday at some point in time. Are there any questions on anything so far?
Can you rewrite the second limit law?
The second one? Yeah, sure.
Thank you.
Remember, if you haven't done so, get into that WebAssign. The directions for that are found on Canvas under the, I believe it's the Pages tab. I have a little guide as to how to get you in there. Make sure you're using Google Chrome or Firefox as you're signing in. As far as that student access code, yes, at some point you do need to purchase it, but everybody has I think it's a 14-day free trial. So you should be able to log into that. The homeworks are up there. The homeworks are basically due the day of the tests. So those due date that you see, I think it's a couple weeks from now or 2.5 weeks from now, that's when your first test will take place. So you'll always know when it's coming up.
Say that again.
As far as what? The due
About the
date?
test?
Yeah, the test. If you're ever in doubt about when the test is going to come up, check your due dates on WebAssign. Like right now, there are the due dates. The homeworks, I believe they're due at 2.5 weeks from now, or about 2 weeks from now, and that's the day that you'll take your test. So instead of us logging in and having a Zoom session, you'll take your test instead during this time on Canvas with the Respondus browser. You can also look at the syllabus too. That's posted under Canvas under the Files tab, because it gives you a week by week guide of what we're going to be doing. So you'll always have like a rough estimate of when the test is, because it'll say week 1, week 2, we do these sections, week 3, test 1, blah, blah, blah. So that way you'll always have a rough idea of how long it will be between the tests. But WebAssign will always tell you exactly the day that you'll take your test. Any other questions right now? Or if you have any questions about anything and something pops up later, you can email me through Canvas, right? Or pop in during the office hours to go out there and ask me as well, okay? If there are no further questions, I will see you guys on Wednesday, all right? Take care.